My name is Terry, and in this video we're going to learn how to convert double integrals in rectangular form over to polar form. So rectangular form is when your integral, when you have x's and y's, when you're dealing with x's and y's. Polar form is r's and thetas. That's going to be converted over from the xy plane to the polar grid. All right. So first thing we need to recall from pre-calculus class are the polar conversions. All right. So your polar conversions. How do we take the x's and convert them to r's and thetas? How do we take the y's and convert to r's and thetas? So here are your polar conversions. And again, from if I can try to squeeze in here and just give you a brief review. All right. From your pre-calculus class. Okay. So if you remember, you recall you studied your unit circle. All right. In your unit circle, we can draw a triangle in here. All right, so this is a right triangle in our unit circle. I'll put a theta right there. Okay, unit circles. So radius of your unit circle is notated by the hypotenuse of this right triangle. Okay, the horizontal segment we call x, and the vertical segment we call y. All right. So it's just x for the horizontal segment, this side of the right triangle. The other leg of the right triangle is y. The hypotenuse is the radius of your unit circle, so we call it r. All right. So the cosine of the angle. Okay. So if you remember from geometry class, cosine of the angle. So your cosine of angle theta, well, it's always represented as your adjacent side over your hypotenuse. Okay. So what is the adjacent side here with respect to theta? The adjacent side is x. The hypotenuse is r, so you can see that cosine theta is x over r. If you wanted to solve for x here, you would multiply both sides by r, so you can see that x would equal r times the cosine of the angle. So your conversions come from your study of your unit circle back in your pre-calculus class. Same can be done for the sine function. Your sine function is the opposite side over the hypotenuse, so the opposite side is y over hypotenuse is r. When you convert that over, when you multiply both sides by r, your y-coordinate conversion is going to be r times the sine of theta. All right. This is a right triangle, so right triangle, your Pythagorean theorem holds. The sum of the squares of the legs of a right triangle always equals hypotenuse squared. So x squared plus y squared equals r squared. And then your tangent function. Tangent is the opposite side over the adjacent. So your conversions from rectangular to polar come from your unit circle relationships between the sides of the right triangle when you put relationships in there. So we're going to need to know these conversions because we'll have to use these conversions as we set up our double integral in terms of polar. Okay. So when you're converting your double integral into polar, rectangular, you have x's and y's, okay? So you can see from the conversions we just went over, you're going to take the x and convert the x's to r cosine theta, all right? You're going to take the y's and you're going to convert the y's to r sine theta. All right, now what about the dA? If you remember from a couple of videos ago when I was explaining the dA, that is representing area of the base. Remember, the double integral is going to find the volume of a solid under a surface, okay? Finding the volume of a solid under a surface, we're going to need to utilize the area of the base times the height. That's what we were using to use the rectangular form, okay? So now what happens is when you convert rectangular, area of the base, because we were using prisms and they were rectangles, when you convert rectangles over to polar, they're not rectangles anymore, okay? You don't have a rectangle here. As a matter of fact, you have a little arc length component involved in one of the dimensions of your, with the area of the base, okay? So the dA, you have to incorporate the arc length component. It's not a rectangle anymore. Arc length is going to be m over 360 times 2 times pi times the radius. So, I mean, it's arc length, okay, the length of the arc is a fraction of the circumference of the circle, and that's the other dimension you need. So when you go ahead and compute your dA, okay, when you compute your dA for polar form, you're going to have your d theta, the change in theta, being multiplied by the dr, but you have this other factor of r that has to be in there because you're not dealing with the rectangle anymore. All All right, so in rectangular form, area of the base times the height, we're using rectangular prisms. So the area of a rectangle, so dx dy or dy dx, okay, the 2 dimensions times the height will give you that feature. All right, however, in polar, it's not a rectangle anymore. You have to incorporate the arc length of the arc length is one of the sides when you're dealing with the dA for polar form. So it's not, you can't just change dy dx to dr d theta. You have to also include this extra radius in here. The extra radius is the arc length parameter that is needing to be included because your rectangle turned into a circular form. All right, so hopefully you can see that here. All right, so we'll be doing the conversions. Okay, so dA is going to be converted to r dr d theta. We're going to take dA and change it to r dr d theta. Okay, the integrand, all right, the integrand, your multivariate function, you're going to take the x's and convert the x's to r cosine theta. You're going to convert the y's to r sine theta. All right, now what about the bounds? Okay, so what about the bounds? Well, your inside bounds are going to be representing the radius, okay? The inside bounds are going to be representing the radius, providing you have a circular base, and they'll get a little bit more complicated when you start dealing with rose curves and cardioids and some of the other lemniscons and things like that, okay? But for right now, we're just going to do some circular bases. So your inside bounds are going to just be representing the radius. Your outside bounds, alpha to beta, are going to represent the change in the angle. All right, I have an example ABC set up on the board. Let's just, before we do our 2 real examples where we have to set everything up ourselves, let's just do a quick little practice with the bounds. Okay, so just with the bounds. So we're going to have, start with example A over here. All right, so take a look at the diagram. Okay, so the radius, it's the circular base. These are all circular bases. Okay, try to draw them circular, so pretend if they don't look circular. So circular base, okay, so now what about the radius? Okay, the inside bounds represent the radius, and so we're going to go from the origin out to 2, so 0 to 2 for the inside bounds for example A, because that's what the radius representation is, okay? Now what about the outside bounds, okay? So the outside bounds, look at where I'm only shaded in the first quadrant, okay? So remember how our unit circle works, how as you rotate around the axes, okay? Because we're dealing with polar axes, we're dealing with polar, so you're going to start here at 0, all right? And then this is a quarter of, so this is pi over 2. All right, half the circle is pi, okay? Then you get to 3 pi over 2, and then 2 pi would be a complete rotation around the circle, okay? So pi over 2 to pi, 180 degrees is pi radians, okay? And so on. So we want to, and we're going to work in radians, so where are we right here? Well, can you see we're just in the first quadrant, so for the theta bounds, we're going from 0 to pi over 2, so 0 to pi over 2, and that's how you would set up the bounds for example A. Okay, the radius 0 to 2. You're going to go from the center of the region out to the region, so we want to represent what the radius is, and then the outside region 0 to pi over 2. Okay, let's take a look at example B. All right, so example B, this is at 1, and this is at 3, so this would be over at -1. This would be at -3. Okay. And these are circular, right, circular regions. So what about the inside bounds? What about the radius bounds, okay? Well, the radius goes from 1 to 3 here. Look, we're in the shaded region. We're going to go from circle 1 to circle 3. So the inside bound, the radius bounds, we're going to go from 1 to 3. We don't have anything shaded in here, so we don't want to start at 0. So 1 to 3 for the radius bounds. And then what about theta? Shaded region starts here and travels all the way. It's half the circle, isn't it? Okay, 180 degrees, when we write that in radians, that's going to go from 0, the shading starts at 0, goes all the way around to pi, okay, so from 0 to pi, and so those are your outside bounds, okay? All right, and the rest of the integrand is going to be pretty straightforward in terms of setting up. In terms of the multivariate function, again, you're going to change the x's to r cosine theta. That's what the conversion is. You're going to change the y's to r sine theta, all right? And then you're going to change the dA, okay, the area, the dA, the area of the base, to r d theta. Don't forget the extra r in there. The extra r is that arc length parameter that needs to be included, okay? And then one last example here, okay? Looks like the radius of this circle goes out to 4, okay? So your inside bounds are going to be 0 to 4 for the inside bound, okay? And then your outside bound, this is going to run from 0 to 2 pi because you've got the entire disk, okay? The entire disk is shaded there, okay? So here, this is how you would set up the bounds. So here's how you would address the integrand, okay? And here's how you would address your the dA at the end, okay? And then this is how the few examples of how you would set up the bounds, all right? All right, so let me erase this board and let's go ahead and take a look at a couple of examples, all right? Let's look at a couple of examples. I'm gonna erase all this here, all right? And we're gonna look at examples where we have to take rectangular. So we're gonna take the rectangular double integral and we're gonna completely convert it to polar form. Because again, polar form a lot of times gives us not an alternate solution, but it gives us an easier method to solve. Okay, so all right, so example one. We're going to set up our double integral, okay, over a region. All right, the integrand is going to be 2x minus y dA. Okay. And then we need to have a description of the base, okay? So we need to know what r is, okay? So for this example, r, okay, is in the first quadrant. Okay, r is in the first quadrant, okay? We're gonna use the disk x squared plus y squared equals 4, okay? We are going to use x equals 0, and we're going to use y equals x, okay? So this is your first example, okay? We have an integral expression, all right? This would be our first example. We have an integral expression, all right, written in rectangular form. So this is written in rectangular form. We want to set up and convert this over to polar form. Okay, so here we go. So let's go ahead and draw the base first. We have to see the base so we can get the bounds, all right? So we need to sketch this, okay? Our region R, so we can get because we know what to do with the integrand, okay? We know exactly what to do. We're gonna change x to r cosine theta. That's what the conversion is, okay? We're gonna change the y to r sine theta because that's what the conversion is, all right? We're gonna take dA and call dA r dr d theta. All right, we have a circular base here, so that's what you do with the dA every single time. Don't forget the extra r because of the extra parameter that needs to be added for the arc length component. All right, so let's draw this base. Okay, so we're going to draw this base in our xy plane. All right, so first of all, we're in the first quadrant. So first quadrant, we're only in first quadrant. Okay. We want the circle, well, in the first quadrant, it's gonna work out to be a quarter of a circle, okay? X squared plus y squared equals 4, so the radius squared is 4, which means the radius is gonna be 2, okay? So we have this, all right? Now, x equals 0, x equals is an equation of a vertical line. So x equals 0 vertical line is actually going to be the y-axis, okay? X equals 0 vertical line is going to be my y-axis, all right? Then I wanted the line y equals x. Y equals x looks like this right here, okay? So I'm looking for the region bounded by the circle, okay? The y-axis and y equals x, it's here. Okay, it's here in my first quadrant. This is the region, this is where I'm at right here, okay? So y equals x, the y-axis bounded by my circle in the first quadrant, this is where I am, okay? So now let's go ahead and we're gonna write our double integral in polar form, So what do we do in polar form? Let's start with the integrand, we have 2. X is gonna be r cosine theta, all right, minus y is r sine theta, okay? What do I do with dA? It's r dr d theta. Okay, don't forget the extra r. Don't forget the extra r. Okay, so remember that's the arc length parameter that needs to be there. All right, bounds. What about the bounds of integration? The inside bounds are the radius bounds. Okay, so what is the radius? The radius goes from 0 to 2. 0 to 2 for the radius bounds. All right. Now, what about your outer bounds? The outer bounds is going to be counterclockwise motion, where the shaded region. Now, where is the shaded region starting? Okay, y equals x, so where is it starting? All right, it's actually starting at pi over 4. Y equals x divides the first quadrant in half. All right, so, and we know that this up here is pi over 2, so pi over 2, so 0 to pi over 2, and y equals x divides that in half, so your bounds are going to be from pi over 4 to pi over 2. That's what the bounds are, okay? So here is how you completely set it up. This is how we completely set it up, all right? Now what I like to do next is I like to take the r, that extra parameter r that needs to be in there, and I like to distribute it, okay? So I like to distribute it, so we have from pi over 4 to pi over 2, and then we're integrating from 0 to 2. Distribute, so you have 2r squared cosine theta minus r squared sine theta. Okay, so I like to distribute the r d theta. All right, and then we can just integrate. I like to distribute the r to each term so I don't lose it. Okay, and that's always going to be there that you'll need to do. Let's go ahead now. We integrate with respect to r first. Work from the inside to the outside. Okay, so the outer bounds are going to be pi over 4 to pi over 2. Okay, do the integration, so integrate r squared, you're going to get 2r cubed over 3 cosine theta minus r cubed over 3 sine theta. Okay, so this is what we have when we integrate. We want to evaluate this from 0 to 2 d theta. Okay, so we're going to plug in 0 to 2 for the r's. All right, so you're going to have from pi over 4 to pi over 2. Okay, plug in the upper bound for the r, right? We integrated with respect to r, you plug in the values for r. So 2 cubed is going to be 8 times 2, so this is 16/3 cosine theta, all right, minus 8/3 sine theta. And then when you do plug in 0 for r, you get 0, okay? And then, so now we're going to integrate this with respect to theta. Okay, so we integrate with respect to theta. I'm going to have to travel. I'm running out of space, okay? So I'm going to travel since I'm running out of space, okay? So when we integrate this, I'll copy it over, okay? So what do we have here? So we're integrating pi over 4 to pi over 2, all right? 16/3 cosine theta minus 8/3 sine theta. So this is what we're integrating with respect to theta. Okay, so we're going to copy this over, so make sure you copy it right. So integrate cosine, you get sine function. So this is 16/3 sine theta. Okay, integrate sine function, you get negative of the cosine function. So that changes the negative of the cosine, changes this to positive, so positive 8/3 cosine theta. And we want to evaluate this from pi over 4 to pi over 2. Okay, so fundamental theorem in calculus, plug in the upper bound, gives us 16/3 times this sine of pi over 2 is 1, okay, plus 8/3 times the cosine of pi over 2 is 0, okay? And then plug in the lower bound, you get 16/3 times this sine of pi over 4 is radical 2 over 2, okay? Plus 8/3 times the cosine of pi over 4 is also radical 2 over 2. Okay, so when you evaluate this, it looks like we have 16/3 for here, 16/3, okay? And we're subtracting from that, what do we have here over here? We have 16 radical 2 over 6, and 8 radical 2 over 6 is 16 plus 8. So you end up with 24 radical 2, okay, over 6, okay, and this can be reduced, right? So 16/3 minus, and then when you compute this, 4 radical 2, okay? So there's your, answer. Okay, 16/3 minus 4 radical 2. And so this is what your examples, this is what it looks like when you take a rectangular double integral and you perform your polar conversion. All right, so this is example number 1. All right, I've got one more example, so let's do example number 2, so you can see another style of a conversion to polar. All right, so here's example number 1. So just remember that not hard to do. If you have a circular base, okay, circular base, then conversion to polar makes things so much easier. Okay, so it makes it easier to compute your double integral when you have circular regions for the base. All right, so, and it's not bad to do. It just x's go to r cosine theta, y's go to r sine theta, dA goes to r dr d theta. Okay, and then you've got to work with the bounds. And working with the bounds, you sketch your region, your boundary carefully, and then just look at the radius, look at the theta off of the boundaries. All right. Okay. So example 2. All right. So let's do one more example. One more example here. So example 2, the integration. A little bit repetitive, but another example, same process. The integration technique will be a little bit different for the example 2. But setting it up is the same way. Okay, so if you have circular bases, if you don't have circular bases, things will change a little bit, but just going to focus on the circular bases right now. All right, so here's example 2. Okay, so example 2, we're going to have our double integral is going to be cosine of radical x squared plus y squared dA. Okay, so there's our double integral. And so R is a disk centered at the origin, radius of 2. So we're going to see R is a disk, right, centered at the origin. And the radius is 2. So I'm going to sketch it right here. Okay, so I'm going to sketch it right here. Here's the problem, and here's so let me go ahead and sketch the base. Okay, so it's a disk, means it's the entire circle. Okay, so R is a disk centered at the origin, and the radius is 2. It's the whole thing. Okay, so this is what R is. Okay, so it's the whole thing. All right. So let's go ahead, and we're going to take this rectangular integral, and we're going to double integral, and we're going to change this rectangular double integral to polar. All right, so let's change to polar. So we have the double integral, we have the cosine function, okay? And then under the radical, x squared plus y squared. Now, we don't want to change x to r cosine theta quantity squared and y squared to r sine theta. There was another conversion there. Do you remember the other conversion? X squared plus y squared. X squared plus y squared is r squared. Okay, all those 4 conversions that you have those at your disposal when you write your integrals. So much easier to just put r squared here. What if you called x squared r cosine theta quantity squared and y squared r sine theta quantity squared? Well, when you did the work to simplify that, you would see it's r squared. Okay, so this takes care of the integrand. Now what do we do with dA? Okay, dA is r dr d theta. Okay, so this is what we do with dA. Okay, now the bounds. What about the bounds of integration? Okay, well, the radius, your inner bounds are going to be represented the radius. So we have the entire disk. Radius is 2, so your inner bounds are going to be from 0 to 2. You're going to go from the center out to where the radius is. Okay, what about your outside bounds? You're dealing with the entire circle. Okay, all 360 degrees, okay, of the circle, 360 degrees in radians, because we must work in radians, 2 pi radians, okay? So you're going to start from 0, travel all the way around to 2 pi, and so these are the bounds, okay? We can simplify square root of r squared. You got to be careful. Radical with a variable squared, when you take the variable out, you usually need absolute value signs, okay? So the radical square root of r squared technically would be radical absolute value of r, but because our radius is 0 to pi, because we are positive, okay, we can drop the absolute value sign, so we can simplify the square root of r squared. Okay, so we can simplify that. So 0 to 2 pi, okay? And 0 to 2, we have cosine of r, okay, times, I'm going to put this r out front, and then dr d theta. Okay, so I'm just rewriting that, rearranging that. All right, now we want to integrate, okay? So how do you integrate? Remember, we're going to integrate from the inside to the outside. How do you integrate our dr d theta? Okay, so to integrate this, we're going to need to use integration by parts, right? So integration by parts, there's a shortcut. Okay, so there's a shortcut. So I'm going to use a tabular method to make a chart. My chart has 3 columns. The first column is going to be SIGN for sign, and then you're going to have your U column, your DV column. Okay, so SIGN, U, DV. SIGN, you always start positive and then you alternate. Okay, for the SIGN column. Your U column is your algebraic looking function here, R. Okay, take the derivative of the R and derivative of that. Okay, and then cosine R for your dv column. Your dv column, you're wanting to get to v, so you're going to have to integrate cosine r. When you integrate cosine, you get sine r. Okay, and then when you integrate sine r, you get negative cosine r. Okay, all right, so now let's do the integration. Okay, so you do the integration. So the 0 to 2 pi we will take care of, but we're doing the integration here. So your first term is going to be going this way to read your chart and this way. So it's going to be positive r times the sine of r. All right, and then your next term is going to be read this way, so minus 1 times a negative cosine r, so that negative times negative gives you a positive. Okay, so positive cosine r, and then your third column is zeros there, so you stop. Okay, so this is what we get when we use integration by parts, whether you use a tabular method or you wrote it out the long way. Integration by parts, we want to evaluate this from 0 to 2, and then we'll take care of the d theta after we evaluate this. Okay, so we're going to integrate from 0 to 2 pi. When we get to the theta part, okay, fundamental theorem in calculus, plug in the upper bounds, that gives you 2 times the sine of 2 plus the cosine of 2, minus plug in the lower bound, which gives you 0 times the sine of 0 plus the cosine of 0. All right, so simplify here, you end up with, we're going to integrate from 0 to 2 pi shortly. So 2 times the sine of 2 plus the cosine of 2, we have this number. And then this is 0, but cosine of 0 is 1. So minus 0, and then minus the cosine 0, which is 1. Okay, so we have this when we evaluate. All right, integrate with respect to theta. This is just a big constant, so you're just going to take theta, multiply it by the constant. So bring the constant down, so you have 2 sine of 2 plus the cosine of 2 minus 1. All right, so the cosine of 2 minus 1. That's going to all be multiplied by theta, and this needs to be evaluated from 0 to 2 pi. Okay, so when you do plug in the upper bound 2 pi, you're going to have 2 pi times the quantity minus, when you plug in the lower bound 0, the lower bound goes away. So running out of space here, but your final answer is going to be 2 pi times the quantity of 2 sine 2 plus the cosine of 2 minus 1, and that would be your final answer here. Okay, so here's the final answer. All right, so polar conversions, when you have rectangular double integrals and your regions, your base regions are of circular form, all right, polar conversions simplify things tremendously. So that's why it's just know your conversion formulas, know how to set it up. Okay, draw yourselves a picture so you can see what to do to handle the base. And that's it. So I hope this helps with polar conversions from rectangular and double integrals. Thank you for watching, and this concludes this video. I hope this helps, and stay safe out there. Stay healthy. Thank you. Bye-bye.